just say recordings in progress, but okay, anyway. So say, for example, you have this. So we have from like 1 to x, f of t, dt. And let's say f of t, I don't know, let's say it's 2t plus 1. Okay, I'm just making something up, 2t plus 1. Okay, so that's what I'm doing. So if I take the antiderivative of 2t, you guys should know it's t squared. And then the antiderivative of 1 is just going to be t. Don't worry about the plus c because we're doing a definite integral.
Wait, but then what happens when like it was a definite integral, but you still had to like the plus 1/2 with the other one?
That was right because I had an initial condition that.
Don't think about it.
Don't think about it. Yeah,
Okay.
just don't think about it. Well, yeah, don't worry about it.
Okay.
So anyway, but hopefully this makes sense, right? So the antiderivative of 2t is t squared, antiderivative of 1 is t, so the root of these is back to that, and plug 1 in x. So if I plug it in, I get x squared plus x minus 1 squared plus 1, which will be x squared plus x minus 2. So I'm gonna actually answer your question. Yeah, exactly. Like we had a plus 1. It's kind of like comes from this part.
Okay.
Yeah, that's what it comes from. Okay, great, awesome. That seems pretty straightforward, right?
So that's the original function. That's where it's.
Yes, this would be f of x. Exactly, 100% correct. 100% correct.
Or is that FTC?
Well, actually, no. Sorry. That's not f of x. No. What I'm talking. No, you're confusing me. No, it's just this is what we got. Don't ask questions. Let me just get through this. All right. Now, let me take the derivative of that. If I take, because we substitute for it, right? We substitute for it.
So why have to change the first place?
It's so that you don't confuse the let, because if you have an extra x, then you have to somehow, distinguish between those, right? So if you take this derivative, you get 2x plus 1, which is f of x, right? Because obviously, that f of t is 2t plus 1.
Wait.
That's 2x plus 1, right? Okay.
So how is, sorry.
Yeah, go ahead. That's fine.
How is that f of x? And then like, if that's f of x and we have f of t, the starting condition is 2t plus 1, and then we'll keep the exact same thing, but with an x, then why do we do the whole like x?
Okay. Yes, I'm getting there now.
Okay.
Good. So now, what if I'm going to do a couple of like things here.
Oh.
What if I change this to like say a 2?
Oh boy.
Will it matter?
Yes.
No, it won't.
No.
It will not matter. Let's say I change that to a 2. Well, here's what's going to happen.
Yeah, it makes it simpler.
Of course.
No, nope.
Yeah, I only could do Earth 6. So that's going to be 6, right? So I'm just going to change all those. But big deal. Because if I do this derivative, what's going to happen if you do it negative 6?
It just goes away.
It goes away, right? So you still get back to this anyway. So that's why for FTC part 1, this could be any constant. It doesn't matter. Because the whole point is, yes, you do the antiderivative, right? Because it's a constant here. But the big part of FTC part 1 is that I want to do the derivatives afterwards. But if you derivative afterwards, it doesn't matter. It doesn't matter. Yeah, go ahead.
And I just want to forget, but an example too, that's how you got the plus 1/2, and that was a of x. So.
Yeah, that was the area. That was the area. That was the area accumulation function.
Oh, so that's the area.
But remember when I did the derivative a of x, it went away.
Yeah. So
Right.
that's the area accumulation function.
This right here, yes, that's the area accumulation function. If that, yeah. So when you say it was f of x, like you were messing with me.
Sorry.
And unintentionally.
So this is all just like to prove what we would have known, because we could just stop and be like 2t plus x, 2x
right.
plus 1, but all that's just.
Now let me throw you guys another curveball.
Oh man.
Exactly. Let me go back to what we had when we had 1 here. Okay,
Whoa.
it's kind of cool, right? That's why I like doing these things on Zoom. What if I change this,
Oh, gosh. That would be
because this is what the worksheet's going to be about. What if I change that to a x squared?
that changes the derivative.
Yeah.
So then this changes, of course.
That would be x4
That would be x to the 4 power
plus x squared.
plus x squared. Of course, x to the 4 power plus x squared. That's why I'm saying, like, just sit back and relax. You know, I'm recording this so you guys can watch it. Okay, if I take that derivative,
That's different.
that's going to be 4x cubed.
Plus 2x.
Now, of course, that's not f of x. Of course, it's not. But here's what's happening. It actually involves a bit of a chain rule.
Wait, but then
Here's what's happening.
isn't it supposed to get us up above?
Nope. Here's what's happening. So now remember, I'm not plugging in x in, we're plugging in x squared, right? I'm not doing it, so this is now x squared is input. So I replace t with x squared, I would get 2x squared plus 1. And if I multiply by the derivative of x squared, what would I get? 2x squared plus 1
Plus 2x.
times 2x, which gets me to 4x cubed
Oh my God.
plus 2x.
But you kind of lost me.
Wait, so
So-
when you change the x to x,
You change that for limits. So you replace, so we, instead of replacing the t with an x, we replace the t with x squared.
Okay.
But also the fact that this is a differential, you know, this upper limit is a variable that is differentiable. So what you have to do with this is that, okay, if I'm applying t, actually, here's another way to think about it. Let me get my
Oh, it's
markers.
like the chain rule.
Yes, that's it. Here's another thing about it.
Amazing.
So you say t equals x squared, right?
You know, like took the derivatives and we didn't have to multiply.
What's your
by
t
x.
squared x?
But the x cubed is
2x.
No, I get that, but like, because you changed the x and x squared, so I didn't.
See that dt there? It's almost like this dt kind of just gets replaced with that. So what you're doing essentially is that you're trying to get this in terms of x. This is a part that's going to, we'll have more discussion about this later in spring. But the bottom line is that you replace the t with the x squared,
Yeah.
you get 2x squared plus 1. But because that is also differentiable, how come I didn't do it earlier? Actually, I did.
Why?
Why?
I did because when I have plain old x, what's the root of x? So that's why I didn't show it, but it was there.
Oh, yeah.
Wait, I have a question.
Wait, so this is like when we were taking derivatives, it's like you didn't have to do the chain rule with x because it was always.
Yes, yes, that's 100% correct. Yes.
Okay.
So I'm gonna do some examples in just a little bit, but one more question. I'm gonna go ahead.
What is the point then of like plugging it in with like the whole like t in the equation and stuff if you're literally just gonna plug it into that, the original one? Like, what's the point? of-
Exactly. There's yeah.
Oh,
You got it. Yes. That's right. Good.
what?
Why do all this? Exactly. You don't need to do this anymore because once I know that, hey, ultimately I want to take the derivative of this, I just replace this t with this x squared and multiply by.
Oh, so you don't have to do anything.
No,
Yes.
exactly. I'm doing this to show you the brute force that goes into it.
Oh.
But no, you guys never ever will do
This is
this.
like a proof. If I could-
Yes.
Oh.
Good. Good. You guys are getting it. Awesome. It's good.